Good morning, good afternoon, or good evening, depending on where you are, and welcome to the Alanos Group webinar, the RF Supercomputer. I'm Chuck Kelly, your host, and I am very, very pleased to have with me Morten Simonsen, the CTO of the Alanos Group. Hi, Morten.
Hi there, Chuck. I'm very pleased to be here as well.
This is an exciting webinar. I've been looking forward to this one since we first announced our webinars because this is such a unique and creative device that you have made here, and I'm looking forward to peeling back the layers on the onion to show people what is here. So let's talk about what we're going to do. We're going to talk about, of course, our $1 million question, which is almost the same as why a RF supercomputer. So we'll just spoil the surprise there. We're going to talk about the algorithms that make such a device work. We're going to talk about the history of the technology, and then we're going to get into the nuts and bolts of the RF supercomputer and also talk about some specifications and back up a little bit and talk about what we've achieved, what makes it possible to call this an RF supercomputer. And then we're going to take your questions. And you'll notice that on the GoToWebinar application that's on your screen, there's a place you can ask questions, and go ahead and type those in anytime, and when we get to the end of the webinar, we'll try our very, very best to answer all of the questions you may have. If we can't get them all within the allotted time, we will send you emails back with answers to the questions. And do remember that watching this webinar qualifies for a half a credit towards SBE certification under Category 1. So with that, let's get to the $1 million question, which is why does the world need an RF supercomputer, Morten?
Yeah, I'm happy to hear your enthusiasm, Chuck, because for me, it has been the entirety of my life for the last more than 5 years. So living with it daily, I tend to see both the challenges and the hard work involved. And it's wonderful to see and cannot help but have observed your enthusiasm for the RF supercomputer. And of course, I share that, but it's wonderful to see that from somebody outside whom has done the development, the excitement that it all creates.
Sure.
But, well, the RF supercomputer is our response to an ever-changing market of higher and higher complexity. The main idea is that we cannot follow the modern times of development, the speed at which it takes place, by keep on creating dedicated hardware for dedicated solutions. So we had to come up with something else, and that something else is mainly a response to what we have observed when we, for instance, if we take TV, we started off with analog TV in the 50s, which was basically based on single carrier technology, and the entire modulation was no more complex that it could be implemented with the tube technology.
Sure.
Well, no surprise, it's not possible to do the modern modulation standards with tube technology. We see that in the quest for using our scarce resource, which I think I can safely say the radio frequency channel in the air is, that we want to transmit as much as possible through the air, because then what we pay for, we get the most return. And the target is that we come closer and closer to the theoretical limit of how many bits we can transmit per hertz. I think for some it is well known that is a limit that was determined by Shannon. And the algorithms and the modulation methods we use to achieve that, they are gradually, exponentially getting closer and closer to the theoretical limit, and that implies that they become more and more refined and complex. So we see that the algorithms, they simply possess more and more of a challenge to the hardware that they are going to be executing on. So this is one perspective. Another perspective is that our world has become very conscient about our resources, the whole green movement. And in response to this, our industry tried to lower the power consumption of our transmission network. One way of lowering the power consumption is to use amplifier stages, so the transmitters for radio and TV, which uses more and more nonlinear technologies. Here we can talk about the extreme cases, a real switching amplifier, Class D amplifier, which will be very efficient, but also very nonlinear. And then we have interim solutions like the Doherty technology, that even today is not only a peak and a main, but we have 3 and even 4 stages of Doherty amplification. These amplifiers are very efficient with respect to power efficiency, but the price to pay for that is that the linearity is very low. But in order to transmit a very high density of data, we need to have a very linear behavior. So our pre-correction circuits, the pre-correction that pre-distorts the signal prior to sending it through the amplifier, also constantly gets more and more complex and include advanced things as memory effects. And this is almost like tracing a moving target, because as soon as we as manufacturer of the exciters manage to linearize an amplifier, the manufacturers of amplifiers say, well, then we can take it one stretch further, and then the race is on to linearize the next stage.
And it's really amazing what you're talking about. Let's put these things into terms. I mean, not too long ago, it was not unheard of to have a television transmitter with an overall efficiency in the 20% range.
Yes,
And it's
that's
like
only 10 years
doubled or
ago.
tripled that. I mean, it's crazy how
Yeah,
much improvement has been done specifically because of exactly what you're saying. The war between the manufacturers building increasingly nonlinear amplifiers, and you guys coming up with more and more algorithms to pretend that they're linear.
exactly, Chuck. But it's really true. 10 years ago, we were maybe in the low 20s of efficiency, and now state of the art is approaching 60, perhaps even the best, a little more on specific channels.
It's
So
amazing.
it has evolved like crazy.
And it's important not only because people are environmentally concerned, but it's also affecting the bottom line. It's affecting the cost of electricity, which hasn't gotten any cheaper.
Very much so. In fact, if we are green or if we are saving money, it's hard to say what the real motivation is. But as it goes hand in hand, it doesn't really matter so much, I think.
Exactly.
Um, the next thing is that the studio to transmitter links, they are also becoming increasingly complex. Years ago, we distributed analog signals for radio or TV from our studio to our transmission sites. Today, I think especially the STL for the ATSC 3 standard is a very complex TCP IP protocol stack. And on top of that, we are even working on authentication and security layers with IP encryptions and a key system just like internet banking. So
Yep.
these links are also exponentially becoming more and more complex. Another step is that for single frequency network transmission, we require to have a common time reference. And this time reference, of course, it can come from the GPS system, but there's also an increasing tendency to try to obtain it from the IP link. And this possesses some challenges because packages, they have unknown amount of jumps in routers and so on. So technology for that is also becoming increasingly complex. Furthermore, SFN is actually harder to do on the waveforms that was not designed originally to do SFN. Here I think, for instance, about analog FM or analog TV.
Sure.
Those standards, we still want to do SFNs. I remember, Chuck, we had a webinar about that a couple of weeks ago.
Yep.
And since they were not designed to do this from the onset, it is something that we have had to impose on these standards as an afterthought. And when things are like that, they have a tendency to be even more complicated than when they were part of the original specification.
Sure.
Another issue is the network management. We see generally that operators, they like to optimize their network management. Some of them, the big ones, they have like almost NASA control sensors where they sit and watch the network live.
Yep.
And here we talk about SNMP traps and quite a lot of different things that also has an ever-increasing complexity. And further, it is something in a constant evolution, because as an operator see the gains he can have of improving his network management, he often tends to continue more and more in that direction.
Yep.
And then simply just mentioning that I think it is likely sooner or later that the world will actually change the protocol stack from IPv4 to v6. Hard to say when it will happen, but we have to be ready for it.
Right. Has to be built into the design.
Exactly, Chuck. And then the next sentence simply says things that we haven't even thought of yet. And this is because the things I have mentioned here is in reality just the first things that spring to mind. There is simply a general tendency that the complexity and the technology becomes more and more demanding. It's a moving target.
The technology that we're dealing with is a moving target, and it's happening at an ever faster pace of change.
Indeed, and that fast pace of change have shown us at the time. I know we will talk about the history of our products later, but it has shown us that we cannot keep the pace by making specific hardware. So the RF Supercomputer, which is a platform for generating any waveform, it was simply the only logical choice in order to be able to follow the pace. And I think this one sums it up a little bit, that there's this ever-increasing pace of change, and traditional hardware, first of all, it cannot do it, but secondarily, it's simply hard to manufacture hardware at the same speed as the protocols are evolving.
I think one of the things that I see in our industry is that the evolution of technology is moving fast, and the cost of doing an R&D project is large, but the amount of time you get to make profit out of that is shorter and shorter by the day because of this increasing pace of change. So something like this is absolutely totally required.
But luckily we managed to create it. So
yeah, there you go.
Yes.
And it all boils down to algorithms, doesn't it?
It does. I mean, it all boils down to all the different and versatile natures of the different algorithms. And every now and then, some smart head comes up with a new, improved way of doing some functionality. And an algorithm is often described in mathematical terms. So that means the algorithm can be worked out without no thinking about how will this actually end up becoming implemented to function in the real world. Right. It's a piece of mathematics, but when we design hardware for transmitting, we need to convert these mathematics into something that actually does the function. And this is where the challenge is, because some algorithms, they lend themselves to certain natures of processing platforms, and some other algorithms then lend themselves well to completely opposite kind of processing platform. So there's almost a built-in contradiction to the hardware requirements. You need to be able to do anything. The next slides, I think we should run through relatively quickly, Chuck, is just to give, let's just go back to the one we just had.
Okay. All right.
This is a typical bit-oriented part of an algorithm. We see data coming in as bits and going through these mathematical polynomia of XORs within the Galois field, and out comes scrambles data. So this block decorrelates the symbol we transmit from the symbol of the data itself. That was just one very, very small example. But if we look to the next slide, we see this is from the TBPC2TV Modulation standard. We see already this is on a block diagram level. If we were to delve into each block, we would see a very high and a very diverging complexity because each of the block contains very different algorithms.
And this is just a small part of the program that's built into the RF supercomputer.
Exactly, and this is only for DVB-T2. Remember, we also do all kind of other waveforms. So we also need to be able to reprogram the supercomputer to do something completely different than this.
Which is the most complex? Is it ATSC3 because that's the most recent?
It is for sure ATSC3, yes.
Okay,
ATSC3,
I'm going to ask you a question. How many lines of code are in your ATSC3 approximately?
Yeah, about 4 million lines.
Holy mackerel.
Yes,
wow.
And let's hope that we don't produce one error per line.
Exactly. Wow. Yeah. That's amazing.
It's really a lot of code.
Yeah.
Okay, so there's a waste requirement of really diverging specifications to the hardware, and this is what we have to try to anticipate when we make the processing platform.
Yep.
And and then not even just to mention the IP TCP protocol stack. This is just a generic picture showing a standard TCP IP stack, but you can see even that one is very complex. Exactly. It is certainly another thing than when we send analog audio as analog signals to our radio transmitters. Now we have to go through all of this, and again, each block contains certain algorithms. So
and
here we are.
It's not just for the communication of the input data to the exciter, the RF supercomputer, but it's also for the communication of the user interface.
Indeed, it is many things taking place through this protocol. And so what we are looking at here lends itself well to the kernel space of a Linux kernel, but certainly not to an FPGA, for instance. As soon as things can dynamically expand and contradict, then it doesn't lend itself well to dedicated hardware. Then we are more in a software world.
Okay. Let's talk about the history. Now, I know from our webinar last couple of weeks ago that your history started quite some time ago. I mean, neither one of us are young men, but you were involved with Philips and all the things that were going on, from the creation of MP3s and CD players, was happening simultaneously with you working on the very first versions of the analog modulators and things.
Yeah, I should maybe say that our company was working on the analog modulators at that time, because 64 happens to be my birth year. But
okay.
But it's true. I was a research scientist in Philips in Eindhoven, where I worked actually in audio compression.
Right.
And that's the reason when I came back to my home of Denmark, I joined Philips at that time there. But indeed, I started in audio encoding, and then I switched to the channel coding. That is what we are doing now. I can tell you a funny thing, by the way, Chuck. When we were doing this audio coding, it was the early days of that technology. So we had to make a simulation of the human perceptionary system. So how the hearing mechanisms of a human being works. And we had to implement this on hardware that didn't exist. So we built custom hardware, which was in 19-inch racks of all wire-wrapped things.
Wow.
And we competed with the Dolby Labs in the US and with Fraunhofer in Germany for who could make the best audio compression. And the best audio compression is the one with the least degradation of the sound quality.
Sure.
And those this sound quality was evaluated by the state radiophonies of the different countries. And on one occasion, Dolby and Fraunhofer and us, we had to send our equipment to Brazil because the Brazilian state radio, their sound experts had to listen and give an assessment of the sound quality. And because this equipment was so unique, and of course it took huge effort time-wise and money-wise to bring it forth. When it arrived to Rio, there was offered a police escort when he was going to go from the airport to the state radiophony. But the fact that there was a police effort somehow triggered some gangsters that thought it was a valuable thing, and the whole thing was robbed and the policeman killed and the equipment never made it.
Oh my goodness.
Which is actually very awful because this, of course, there was the tragedy of the dead people, but also this equipment could only be operated by my very, very small team. So the net result for the gangsters was absolutely worthless.
Oh my goodness.
Yeah, but
wow.
Those were funny days, and
Yeah.
the result of that early work, all of us know it today because eventually it became MP3 audio compression. So now that was a sidestep. Let's get back to the hardware evolution.
Yeah.
So indeed, we made a dedicated hardware solution for the first analog modulator, and that is also depicted in the top picture. That one could only do analog TV, and it could not be reprogrammed for anything else.
Right.
And then go forth a lot of years to 99. That is the year we made our first digital modulator, or exciter if you want. And there, because we had been living with hardware, we thought we have to have a software solution that will give more flexibility. So we made a very advanced system of having 10 DSPs work in parallel, if you imagine coordinating that. But this was for DVB-T, and that, of course, worked very well. But we realized that having only DSPs really did not give the versatility we needed to implement the next generation of modulation standards, which was maybe not appearing already in 99, but it was beginning to be worked upon in the standardization bodies. But the 10 DSPs we integrated into our own ASIC design, and this made the second generation exciter, which is the one you see on the picture in the middle. And then finally, the first attempt at the RF Supercomputer, the first generation, was finished in 2005. And the system design work was actually an effort more than beginning, I think, late 2002, and involving some 20 engineers. So it was really a big effort to figure out how to make an architecture that can stay with us a long time, even acknowledging that in that time span there will be new requirements to the hardware. So this is where the footwork was done.
Speaking of footwork, let me ask you this question. From 2002 to today, considering the software and hardware engineers involved, approximately how many man years are we talking about?
Oh, that is really a lot, Chuck. It is, let's say, on average, maybe 15 man year for each of the years. So yeah, that's 400 man years, more than 400 man years. Yeah, it's really a lot. Frightening to think about. Yes, it's a big effort and a big investment. So from the 2005, the first platform to the one you see as the RF Supercomputer, there's actually 11 revisions of designs in between those two.
Which are all backwards compatible.
Which are all backwards compatible, exactly true. So
That's great.
the one in the right hand, the lower one in the right hand corner is our current incarnation of the RF supercomputer.
Fantastic. All right, so this is what it looks like in terms of blocks of technology.
Yes, yeah. And let me talk you through it briefly.
Please.
The blue arrows that are accessible from the left, that is all the input-output. So this is the ASI, the SEMTET reading, the analog signals, the digital signals, the IP protocols, the GPS antennas, all the, should I say, backbone signals are there. And to the right, we have the radio frequency signals to the right of the gray box. So that is the output to the amplifier and feedback signals for the linearization.
HPA basically means the transmitter.
Yeah, high power amplifier.
Yep.
And then the channel filter. Looking to the different boxes, we can see the main building blocks of the RF supercomputer. And I will talk you a little through it. There's an ARM microprocessor where I have written bare metal. By bare metal, I mean that it is not running an operating system. We are coding directly on the instruction set of the chip. When we do that, we have 100% deterministic, time-wise deterministic behavior of the software. And this is what you, in other terms, call hard real time. So that means there's one separate microcontroller that has a guaranteed timely response. For instance, you could imagine that through the blue arrow to the outside world, that our exciter is asked to monitor the reflected power of an amplifier. If the reflected power gets too high, we are requested to mute the signal maybe within 1 microsecond.
Yep.
For a Linux kernel, that would either means to do that using an interrupt or using some special hard real-time version of the kernel, which is not so nice to use in all other aspects. So for that reason, we have this dedicated processor that can take care of these hard real-time requirements. Then we have another ARM microprocessor which runs an embedded Linux kernel. That one also runs the TCP IP stack. So that has a lot of, it is actually partly in the signal path when it is doing the scheduling for ATSC 3 or for TBPC2. It also handles the web server and general housekeeping of the entire board.
Right.
And going further up from the ARM microprocessor, there's a digital signal processor from Texas Instrument. That one is also running without an operating system. And the digital signal processor is very useful for linear signal processing. So this can be things like digital filtering or FFTs, for instance.
Sure.
And then we have the FPGA, Field Programmable Gate Array, which is to be regarded as a programmable piece of hardware. So that device is simply a software-defined hardware behavior. So that one we can program to do anything you could do with hardware. So that there we can make really, really special bitwise or whatever kind of algorithms. And exactly the combination of the Linux and the digital signal processor and the FPGA, this is the combination that taken together is well suited to implement whatever kind of algorithm we know today or we will see in the future. Because we can spread out parts of the algorithm to the processing part that where they lend themselves well to be implemented.
It's kind of like the idea of parallel processing, only they're routing the computational efforts to the area that is best suited.
Exactly, Jock. And this is actually the area where we have put a lot of effort, because in order to put parts of the algorithm on one device and other parts on another device, it means that we need to have tools how to, first of all, distribute it to the processing devices, but we also need to move very, very high speed amount of data between the devices. And normally, if you use a communication bus, for instance, then the processing device would use some of its processing power to handle the bus transfers.
Right.
But there we use a system which is also used in computers called direct memory access, and that is a system whereby the transfer of the data between the devices takes place as a background process, so that it doesn't load the processing unit of the specific device.
In
And in
essence,
that way,
these devices, these three devices, have a shared memory space.
yes, you could say it like that, comparable to that. And that means that they are not burdened by moving the data between them.
Sure, makes sense.
Looking further, I also drew part of what is important for SFN, and that is the timing and the GPS. So we can get the 1 PPS and the 10 megahertz external references, or we can connect to an external antenna for using some global navigation system for timing reference. This block by itself has quite advanced holdover and switchover functionality with the priority, so that if a high priority time reference should have an error or disappear, then it will switch to the next priority without interruption of the timing reference.
Wonderful. Yeah.
So that is taken care of in the timing block. The timing block then controls one single reference oscillator. There are three choices of the quality, but it has the functionality of being one single timing reference. And everything on our board is synchronized to that oscillator. So that means we have taken care not to have any power supply switches or local oscillators or anything which is not locked to this oscillator. Because if you have free running switches or oscillators, then you will have beating tones as the sum and the difference of these signals, and that will mean that your RF output is not clear. It is distorted by these things that moves around.
Absolutely.
Looking to the right of the FPGA, the processing part leaves its signal to be converted into the RF analog signals. And that happens through the output go through a couple of DA converters. Then we have a quadrature mixing scheme, and then we have the RF output on the RF channel feeding the amplifier. The amplifier generally feeds a channel filter because we are not allowed to make noise into our neighboring channels. And then we have the transmitting antenna. Then I have drawn here two couplers. So we have the option of taking a feedback, one after the amplifier, one after the filter, feeding back into the inverse signal path, so quadrature down mixing and AD converters, and then back into the FPGA. This up converter and down converter, they work on the same local oscillator, so that potential phase noise in this round going loop will be cancelled out. But that means that inside our system, our processing unit, we now have a sample of what did the amplifier do to our signal? How did it distort it? And also what did the filter do in the amplitude and the group delay domain? And this signal we can use to do our pre-distortion that I briefly mentioned before has also increasing complexity. This is a field we are actually very proud, because I think I know we are state of the art, which means that we can extract the most linearity out of any amplifier compared to any other known technology. And that translates directly into power efficiency and thus savings on the bank account.
And MER.
And MER, yeah, you can use it to improve your MER, or you can use it to improve your efficiency, or anywhere in between. That's a trade-off the user can make himself.
That's right. Okay, so let's talk about the specifications.
Yeah, I just wanted to mention something briefly here. So it is a 16-layer printed circuit board.
Mm-hmm.
And this 16-layer printed circuit board even has what is called buried vias. So that means any layers of the 16 can be connected to any other layer. So it's a 16-dimensional 3D labyrinth, so to say. It's quite an amazing thing. And onto that board, there are more than 2,200 surface-mounted components, and so many components on so little space actually means that it is no longer possible for a guy like me that is more than 50 years old, almost even to see the passive components, for instance. They are so damn small.
Yeah.
We have 5 Ethernet ports, and these have individual MAC addresses. This is not so usual, but when an operator wants to have redundancy in his distribution network, it is very often a requirement that the redundancy includes the fact that the endpoint has to have different MAC addresses.
Mm-hmm.
In other words, a shared MAC address does not qualify as a completely redundant feed,
right,
or reserve feed, or what you like to call it. 100% synchronous, that is what I just described when we looked at the drawing, that everything is synchronous to the same oscillator. Yeah, exactly. The radio frequency output can be in the range from 30 megahertz to 760 megahertz in 1 hertz steps.
Wow.
And I should add to that is actually our standard range. We have an option of stuffing the board differently in case some customer would like to use it for L-band or something else.
Mm-hmm.
The board is supplied by a single supply voltage that has to be in the range from 5 to 50 volts, and then we regulate anything to what we need internally.
Sure.
We can fully firmware upgrade the board even remotely, and that actually means, for instance, this could be interesting for the US market, that a transmitter we install today operating in ATSC 8VSB is 100% future-proof if the US should move to ATSC 3, because in that case, it is simply a matter of changing the firmware of the RF supercomputer.
That's right. Yep.
Which
or it could be updated to something that hasn't even been defined yet.
Exactly, some future standard. Or US could become part of Japan, and then it would be ISDBT.
Yeah.
Maybe a little too speculative, but in fact, the board is completely software defined, and that is why we can define the behavior through loading software onto it.
And in fact, this box is really, when you think about it, using the technology, the words of the moment, it's an SDR and an SDT. So it's an SDT in its most basic sense because it can create all these signals. But because it's got the reverse path, because it can do the adaptive pre-correction, it's actually an SDR as well.
That's true, sir.
Mm-hmm.
I talked about REST, I think. Also, of course, there's the web server, where we have actually taken a little bit care not to use Flash or Java or anything that requires a browser to have a plugin.
Yep.
So any standard browser you can connect, and it will work without saying please download or no support for.
Right. And we're actually going to have a very brief walk through the user interface in just a moment.
Yeah, we'll show some of it indeed.
Yep.
We have these 3 levels of reference oscillator that I mentioned. So by level, I am implying the amount of time a free-running oscillator can keep the waveform valid for a SFN network without drifting away.
Right.
There are quite strict requirements in some countries, the worst being 24 hours. So if you imagine you are timed in an SFN network where the timing requirement likely is something like 100 nanosecond precision, and you lose the signal that you are locked to, you lose the lock to the external reference or the GPS, and then a holdover function of the internal oscillator will take over driving the machine, and that has to stay within the specification of the SFN network for 24 hours free running. So
Amazing.
that is the highest level of oscillator we have, but I can tell you it's a double oven and a very complicated thing.
I imagine so. Yeah.
And then
And
I
of course, all the
briefly,
standards. Yeah.
yes, and then all the standards. I think our viewers, they can read them, but we do support really quite a lot of waveforms.
Right. And basically all digital radio and digital television, and some analog as well.
Yeah, that's
So
true.
pretty much everything. You can
Yeah.
come up with the waveform. We can make it happen. Okay. So thanks for that. Let's see. So the RF supercomputer is.
Yeah, consisting of this hard real-time processor we spoke about,
Mm-hmm,
also a Linux real-time multi-threaded processor, a
mm-hmm.
programmable DSP, and a very large programmable FPGA. And that together is the powerful combination that when we tie it together with this direct memory access system in combination with our way of spreading out the algorithms, then we have this very, very powerful machine for doing all existing and, to the best of our fantasy, also future waveforms of modulation.
Sure.
It gives us, of course, when we make such a board, the initial investment in architecture and research is really magnitudes larger than when you make, should I say, a traditional piece of hardware.
Sure.
So the payback that we experience, that is that we will end up having a faster time to market because our hardware is already done. Furthermore, when we support all these many waveforms, for instance, the pre-corrector is always the same. The TCP IP protocol stack is always the same.
Mm-hmm.
So we end up having a lot of reuse, which works very constructively for us because it also means that if there should be an error, let's say an error in the IP protocol stack, when we improve and fix that error in the waveform where the customer reported it or we found it ourselves, then when we improve that in the driver and commit the driver back to our software repository, automatically that fix affects all the standards without any additional work from our side.
Yep.
And that way of working means that once we have built up the basic things that goes again from system to system, waveform to waveform, we free our minds from doing the trivial tasks over and over again and release our time and mind to work on the interesting stuff,
The
which
creative stuff. That's right.
makes our engineers happy and also makes that we keep this fast time to the market at the same time.
Absolutely. So let's go, and I'm going to hand over the control of the webinar there to you, Morten, and let's let you show us the user interface, if you don't mind.
I don't mind at all. I see you have handed it over to me, so now I will see if I can manage to show you something useful.
Okay.
I hope that you have our web GUI on the screen now. Is that true?
I do. I just got it.
That was
Thank you.
perfect.
Murphy
So
was thwarted.
this is this product is ATSC 3, but do remember it is just the firmware I have decided to load into the machine.
Okay.
But this web GUI is representative of how the web GUI looks for all of the equipment on the supercomputer. In the upper half, you see a signal path, and that signal path starts to the left and ends to the right. So
Yep.
We see that the Ethernet 0 port is used as input on input RX1, and this is where the STL, the studio transmitter link, is connected.
Yep.
Then we have in the input block some switching, because we can switch seamlessly between several feeds in case it is a transmitter where the customer wants to have redundancy in the feed. The mode block is where you set up the modulation parameters. And mind you, this being ATSC3, I will not show you too much of that because it is an extremely versatile. I just show you a little bit of the mapping and some of the configuration of that here.
Wow.
That can be quite complex, but this is standard specific. Then we have the pre-correction block, where we have the linear pre-corrector. We have the linear pre-corrector will linearize the channel filter in magnitude and group delay. Then we have a clipping block, which is grayed out because I'm not using it right now. That block is used to reduce the crest factor of the output signal. Then we have the nonlinear pre-corrector. This is the one that linearizes the amplifier. And then we have the OptiPower adaptive algorithm. This is what actually does the clever stuff of extracting the highest possible linearity out of the amplifier.
Yep.
And then the final block to the right is the where you set the frequency and the level. If we then look to the lower half, these kind of three vertical fields are in fact identical. So the concept is that you realize you want to change something in some block, then you can take the block and drag it with the mouse to any of these three fields. And when you let the block go, it expands and show
Sure.
into the details. So now just to demonstrate that these three vertical ones are the same, I opened the same thing 3 times. But I can put the pre-corrector there and maybe the output to the right. So the output, you see, you adjust the frequency here and the bandwidth of the signal and all these on-air parameters, the level. In the middle one, where you see the spectrum, of course, to analog radio and TV people, this is a weird spectrum, but for coded orthogonal frequency division multiplexing, this is how the spectrum looks. And the bandwidth of the channel here, I don't know the specific mode, but I think we can probably have 32,000 carriers here.
Right.
Over the 6 megahertz channel. This spectrum is a measurement of the actual output of the transmitter. So the RF output here in the lab, this equipment is standing in my lab in Copenhagen, and I'm currently in Italy, and I'm sitting as if I was at home. And any operator could sit anywhere and log on with a secure password and get this web access. The RF output is feeding an amplifier, and then there is a coupler giving the signal back to this nonlinear sense input. And thus the spectrum we see here is the spectrum that the amplifier is producing. Also, if we look to the left, we can see that we also measure the performance parameters. We have an MER of 43 dB and the upper and the lower shoulder of more than 46 dB. Just to give you an idea of how powerful this is, Chuck, I could try now to push a button so that we would put a neutral pre-correction. That means just to disable the pre-corrector.
Wipe out all the things that it had already learned.
All the things that it had learned automatically.
About the amplifier. Yep.
Yeah. So next time we see a spectrum, we can see what the performance is. I would just like to show you also that we have, of course, SNMP, we have LAN, we have many things. We have an alarm system that is highly flexible and programmable. Now I have expanded the alarm system, and we see there's alarms for the reference system, the primary input, the secondary input, the RF output, IP alarms, external alarms. Those are external events to us, monitoring the hardware, communication, and internal alarms. But all of these are groups of alarms. So if I expand, you can see how much they obtain. And then there is a configurable matrix. If you want it written to the event log, you want to trigger one or two or both output alarm relays, or have an SNMP trap, even have an email or turn on the alarm LED. So this flexible system makes it possible for an operator to tailor the behavior as to what he finds a serious event and what he finds a less important event.
Mm-hmm.
Here you see the starting point of our pre-correction, and you see we are at 24 dB. So this amplifier, which is a Doherty amplifier, we actually improved the linearity from 24 to 44 dB in MER.
20 dB improvement.
Yes, and
But
for
it
the
takes
amplifier, it takes this one takes about the first iteration is a little longer. That takes 79 seconds, and then the next iterations they are around 50 seconds. And after let's say 5-10 iterations, you have very, very good performance.
Excellent. So just in a few minutes, it's amazing to think about all the adjustments and corrections that are going on. You couldn't do it. You couldn't do it with a little green screwdriver.
That's true, Chuck, and you couldn't do it in that time. That is one thing, but the complexity here also include memory effects and so on, which is not at all intuitive to trim by hand at all. Can only be done by a computer.
Now we've gone up to 31.7, so we've added almost another 10 dB.
Yeah, so you see that is going quickly.
That's great. Thank you.
We have here the point where we upgrade the software, and actually you can see there are two software images on board at the same time. So we have booted on ATSC 3, but actually in the other image we have a digital audio broadcasting version of the software. So this one I could reboot into DAB, but I could also press the browse and then direct the machine to any other firmware, and we could put any existing or indeed, as you said, Chuck, potential future software and go on here with that.
And in fact, somebody could have, let's talk about ATSC 1 or the legacy ATSC in the US. Somebody could have bought that 5 years ago, put it on the air, and in the future, they could download, pay for the licenses and stuff, but download the ATSC 3 image, put it on, and now they've got an ATSC 3 system.
That's very correct. So I think that is a reflection of the versatility of making this RF supercomputer. So in the beginning, it was an initial very big investment and effort. Of course, it is still a big effort, but it has given us so many advantages that exactly is passed through 100% to the customer as well, because he can tap into this flexibility and buy a future-proof machine.
That's amazing. That's wonderful. We're running a little long, so I'm going to go ahead and bring this back and show our PowerPoint again here. Let's see here. It's right here. And, oops, it took me back to the beginning. Didn't want to do that, but let's see if I can make this. Okay, there we are. So to wrap up, the Protelevision Elenos Group RF supercomputer is really powerful. I don't know how else to say it. And it's programmable for any known RF, TV, or radio modulation. It operates from 30 megahertz to 760 megahertz. It includes all of the satellite timing standards that are included in the GNSS timing protocols. It allows advanced PAPR for improved efficiency, includes powerful signal analysis, which facilitates the pre-correction that we've been talking about, includes a dedicated web server for monitor and control that doesn't include flash. It's field updatable for technological advances and new protocols. It's designed to be fed by IP or other inputs. And the RF supercomputer is or will be the basis of all Elenos, Itelco, and BE transmitters. So now let's see what kind of questions people had, and we'll try to answer a few of these before we head home for the evening here. Let me pull that out.
Actually, Chuck, I would even like to add, when you mentioned the GNSS, that is of course perfectly correct what you are saying, but we can actually do any combination of any two of those standards. For instance, GLONASS and GPS at the same time, and then switch from the one to the other without interruption of the service.
We have one question here. This gentleman has several PT200 units. Are there firmware upgrades available for those boards?
Of course, that depends on the year they are from, and also which firmware the gentleman is looking for.
Sure.
We did have to increase the size of the FPGA when we moved from the first generation to the current generation.
Yep.
So I would be happy to answer a very specific question, but
I'll put you in touch with John, and you can answer him directly and have that information go back. So that was the only question I had here. So let's say we will say thank you to everybody. We know how valuable your time is. We're honored that you spent some time with us. Thank you so much, Morten Simonsen, for this fascinating discussion. I never knew a single PC board could be so powerful. Thank you, everybody, for being with us. Morten, thank you again.
And thank you, and thanks to all our listeners.
And for Morten Simonsen, I'm Chuck Kelly, thanking you for being with us. Have a good day. Bye-bye.
Bye.